9b energy, 9.9 kinetic energy. A force performs mechanical work on a system in order to move the system from one place to another. Motion implies that the system has a velocity, and changes of motion imply accelerations. Moving objects can do work when they strike something else. Just consider the damage a flying baseball can do to a window pane. Evidently, a moving object possesses the ability to do work. This mechanical energy associated with motion is called kinetic energy K. Kinetic energy is a positive scalar quantity measured in joules in the SI. The work energy theorem states that the total work done on a system by all the external forces acting on it is equal to the change in the system's kinetic energy. W total equals delta K, or W total equals K 2 minus K1 9.8. From Newton's second law, you know that sigma F equals ma. Now the work equation can be rewritten as a first law expression. W total equals sigma FMD equals MAD 9.9, where sigma FM is the sum of all force components parallel to the movement during the displacement. D. From the third equation of motion, you know that D equals open parenthesis V squared square minus V 1 square close parenthesis over 2 a bar. Multiply both sides by a bar D equals open parenthesis V squared square minus V1 square close parenthesis over 2. Substitute for add in the right side of equation 9.9 and distribute the terms. W total equals M1 half V 2 square minus V1 square. W total equals 1 half the MA MV squared square minus 1 half the MV1 square 9.10. Comparing equation 9.10 to equation 9.8, it seems logical to define kinetic energy as K equals HMV square 9.11. 9.10 potential energy. Not all work changes kinetic energy. Suppose you slowly lift a box from the floor at a constant speed to a height that will allow you to place it on a shelf. If the speed of the box is uniform throughout the lift, the kinetic energy of the box does not change. The work simply changes the position of the box. However, before you lifted the box, it had little potential for falling unless there was a hole in the floor. Once on the shelf, the box has a greater potential for falling to the floor. If it were to fall, its kinetic energy would increase as gravity did work on the box. While it rests on the shelf, therefore, the box is said to have gravitational potential energy. Potential energy, U, is energy due to an object's condition or position, relative to some reference point, assumed to have zero potential energy. As with kinetic energy, the unit of potential energy is the joule. There are other forms of potential energy besides gravitational potential energy. They include elastic potential energy, which comes from the forces between atoms, and electrical potential energy, which comes from the electrical forces between charges. Potential energy results from work done against a force. For example, the box was lifted to a shelf, increasing its gravitational potential energy by working against gravity. Similarly, a spring is stretched by working against the elastic spring force, thus increasing the elastic potential energy of the system to which it is connected. 9.11 Conservative and non-conservative forces. Not every force has potential energy associated with it. Only forces that are conservative forces have their own potential energy. A force is a conservative force if either of the following two conditions is true. The network done by the force on a system as it moves between any 2 points is independent of the path followed by the system. The network done by the force on a system that follows a closed path is zero. A system follows a closed path if it begins and ends at the same point in space. Some examples of conservative forces are the gravitational force, any central force, a force acting between the centers of two systems, any Hooke's law force. Conservative forces are so named because the energy expended when doing work against them is stored as potential energy and can be regained as kinetic energy. Other forces do not have these attributes. If the network done by a force on a system over a closed path is not zero, or if the work done by a force on a cistern between 2 points depends on the path taken, then the force is a non-conservative force. Examples of non-conservative forces include kinetic frictional force, internal resistance forces, e.g., spring internal resistance, fluid drag. When work is done against non-conservative forces, the energy is not stored as potential energy, but is converted into other forms of mechanically unusable energy, such as heat, sound, or light. 9.12 Gravitational potential energy. All masses, from atoms to galaxies, exert gravitational forces on other masses. If the masses are separated, then the gravitational attraction tends to pull them together. Thus, two masses separated by some distance have the potential to be drawn together by the gravitational force exerted between them. The work required to move these masses apart against the force of gravity is equal to their gravitational potential energy. Near the Earth's surface, the force of gravity on an object is nearly constant at Fg equals mg. The work done against gravity in lifting an object at constant speed goes entirely to increasing the object's potential energy. Consider an elevator of mass m that is lifted with constant speed from a height h to a height h2. Since the elevator's velocity is constant, the acceleration is zero, and there is no net force on the elevator. That is, the lifting force just balances the force of gravity, or the elevator's weight, neglecting frictional forces. The lifting force must therefore have the same magnitude, but opposite direction as the force of gravity. F lift equals negative Fg equals negative milligrams. F lift equals absolute value of mg upward. The work that the lift cables do against gravity in lifting the elevator is equal to the product of the force they exert on the elevator and the elevator's change in height. W lift equals F lift. D equals absolute value of mg times open parenthesis h2 minus h1, close parenthesis times cosine of 0 degrees. W lift equals absolute value of mg delta h. Since the force of gravity opposes the lifting force, their components along the direction of the elevator's motion are opposite. Therefore, the work that gravity does on the elevator as it rises is negative. Wg equals Fgd equals absolute value of mg times open parenthesis h2 minus h1 close parenthesis times cosine of 180 degrees. Wg chu minus absolute value of mg delta h 9.12. The elevator's potential energy, Ug, changes by the amount of work the lift cables do on the elevator. Delta Ug equals W lift equals Img delta H, 9.13. Does it make any difference whether the change in height begins at the Earth's surface or at 10 meters above the surface? No, as long as the object stays near enough to the Earth's surface so that Fg equals the absolute value of mg, there is no significant difference. If you compare equations 9.12 and 9.13, you will notice a fundamental relationship between the work done by a force and the potential energy associated with that force. In the case of the gravitational force, Wg equals delta Ug, 9.14. Equation. 9.14 is true for any conservative force. In words, work must be done against a force in order to increase the potential energy of a system with respect to that force. Conversely, as potential energy of a system decreases with respect to a force, the force does positive work on the system. Notice in part C of the previous example that the work done by the lifting force is compared to the change in potential energy with respect to the gravitational force. In this case, both are positive. The work of one force on a system often causes a change in potential energy with respect to another force also acting on the system. You must be careful when working such problems, so that each force is correctly associated with its corresponding work or energy. 9.13 Relative Potential Energy. What is the gravitational potential energy of the book in example 9.7? The gravitational potential energy of a system is measured by the amount of work gravity can do on it in the absence of any other restraining forces. Since the force of gravity on an object is constant as long as it is near the Earth, the work gravity does varies only with the distance the object can fall. So we could say that Ug sarp LMGHH 9.15, where h is s, the distance that the object can fall. How far can an object fall? Figure 9 to 16 points out the difficulty in answering this question. A rock rests on the edge of a cliff. What is its potential energy? It depends on your height reference point, the point from which you measure h. If you believe the rock cannot fall at all because it is firmly wedged in at the top of the cliff, then h equals 0 meters and UG equals 0 joules. If you expect that the rock could fall to the tree, then the tree is the height reference, and the rock is at h equals plus 10 meters. So UG equals 10 absolute value of mgj. If you think it's possible that the rock could fall to the surface of the water, then the water's surface is the height reference. The rock's height is h equals plus 40 meters, and UG equals 40 millijoules. If you allow the rock to fall to the bottom of the river, then its height is h equals plus 50 meters, and UG equals 50 millijoules. Which value of the potential energy is correct? Each of the values of potential energy is relative to the selected reference point. Since you need to know only the change in potential energy, delta UG, which reference point you choose does not matter. However, after choosing a reference point, you should use it consistently throughout the problem. 9.14 Gravitational Potential. Gravitational potential energy depends on the mass of an object and its position within the gravitational field. The strength of a field is measured by the force it exerts per unit mass. For locations near the surface of the Earth, the gravitational field strength is simply 9.81 newtons per kilogram. So the gravitational force on an object, or its weight, is the product of the object's mass and the gravitational field strength. Fw equals m times 9.81 n per kilogram equals the absolute value of mg. Similarly, the gravitational potential energy of the object is the product of its mass and its gravitational potential, UGR, which is defined as its potential energy per kilogram at a specified distance, r, from a zero reference distance. For locations near the surface of the Earth, UGR is simply GH for any mass m. But what if you want to calculate an object's potential energy at some location where gravitational field strength is not equivalent to the absolute value of g, i.e., Fw is not the absolute value of mg? You can find the work done by any gravitational force by using a force-distance curve. You learned in Chapter 7 that the gravitational force between two objects can be calculated from Newton's law of universal gravitation, Fg equals gmm per r square, where r is the distance between the centers of the two masses. The force that one mass exerts on another is plotted versus distance in Figure 9-19. Suppose that mass m starts at a distance r from mass m and moves away at a constant velocity. A force with the same magnitude as the gravity between the masses, but with the opposite direction, must move m. The work that this force does is equal to the shaded area in Figure 9-19. Calculus shows that the area is equal to Wext equals gm per r. Since the work was done at a constant velocity, delta K equals 0 joules, it all became potential energy. The change in potential energy of m is therefore delta UG equals gmm/r, 9.16. For gravitational potential far from the Earth, as well as for potential energy near the Earth, the reference point is arbitrary. However, in general gravitational problems, it is customary to choose the potential energy at an infinite separation as the zero reference point. For any distance r between m and m, delta UG, UG, infinite, UGR, delta UG, 0 minus UGR, where USR means the gravitational potential energy at separation of. Therefore, substituting for UG back into equation 9.16, UGR equals gmm per r. UGR minus g mm per r 9.17. Since the constant g, the masses and the distance are always positive, gravitational potential energy is negative for any measurable separation distance. However, increasing r decreases the absolute value of UG, making it less negative, so potential energy is greater, less negative, the farther apart the two objects are. Consequently, the gravitational potential energy per unit mass, for any object of mass m at any distance r from mass m is simply UGjar equals negative gm per r, 9.18, where m is the source of the gravitational field and r is the distance from the center of mass of the source. The unit of gravitational potential is joules per kilogram. 9.15 Gravitational work function. How does the change in gravitational potential energy relate to the work that gravity does? Remember that the external force that pulls m away from m is equal in magnitude but opposite in direction to the gravitational force between the masses. So their components in the direction of motion are opposite. Therefore, Wx equals Fe xd equals negative Fgd equals negative Wgg. The change in potential energy is delta UG equals W, x equals negative G. Delta UG equals negative Wg, which is essentially the same as equation 9.14. Recall that gravitational force is a conservative force, so the work and change of potential energy does not depend on what path the masses take as they move toward or away from each other. 9.16 Elastic potential energy. Elastic forces in metals come from the tendency of a metal's atoms to remain at a fixed distance from one another. If the atoms are pushed closer together, they repel each other. If they are pulled farther apart, they attract one another. That is why spring pulls or pushes back to its equilibrium position if it is stretched or compressed. External forces work against the spring force as the spring is stretched or compressed. Therefore, elastic potential energy can be produced with respect to spring-like elastic forces, which are conservative forces. The work done by an external force, Wx, against an elastic force to stretch or compress a spring at a constant velocity is equal to the change in the spring's elastic potential energy. The amount of work needed to stretch a spring from a length of x squared to a length of xs is shown as the lightly shaded area in Figure 921. Both lengths are measured from the spring's equilibrium position, x1. This area is equal to the area of the large triangle minus the area of the small triangle, wx2. 3 equals delta us equals 1/2 kd 2x squared minus 1/2 kd 1x squared. W x2 to 3 equals 1/2 kd squared x squared minus d 1x squared. If the spring begins at its natural length, x1 equals x2, then d1x is 0 and wx equals 1/2 kd 2x squared. Once again, we determine the work done by an external force on the spring by evaluating the change of potential energy with respect to the elastic force.